It's a great pleasure to announce the first speaker of the afternoon, Miquel Cueca from the University of Göttingen, who will tell us about sigma models and Lie bialgebroids.
Okay, so thank you very much. It's a great pleasure to be here. I think that as all we say, being in a conference in presence after COVID, it's something really important. So I also want to agree on that. So what I want to talk today is about the interaction between sigma models and Lie bialgebroids. And in fact, at the end, I decided that I just will talk about Lie bialgebras to make it easier. So this is a joint work with Alejandro Cabrera that is in Brazil. And well, let me say some key things. So as we already saw it here, normally there are two aspects that always play a role in all the talks. One is the geometry, and what we will look is into a particular kind of Poisson manifolds that are the Poisson Lie groups, and the infinitesimal counterpart that are the Lie bialgebras. And the second role is which is the quantization technique that we will use to work with this particular kind of Poisson manifolds. So what you should expect is some kind of path integral approach to quantization, or also known as topological quantum field theories. In particular, Poisson and Chern-Simons sigma models is the one that will play a role in our work. So that's basically the two building blocks of our work. One is the geometry side, which is the ingredients that we need, and the other, which is the quantization technique. And I want to say that I listened to Pavel Severa once that in quantization, we should not be afraid of which is the quantization technique that we use as far as it produces interesting answers. So in somehow, you see, the different motivations that you can have is depends of if you care in geometry or in topological quantum field theories, but the result that we have is of field theoretic nature. So will be like path integral result, and therefore is not, let's say, a mathematical proof, even though some kind of mathematical arguments can be made really precise. But the interesting that is the quantization at the end is of field theoretic nature. But I think that will produce some kind of interesting answers. And maybe to just motivations is, on one hand, if you care about geometry, you can just ask about, well, what can we say about the quantization of Poisson Lie groups or the quantization of Lie bialgebras? And in the other hand, if what you care about is about topological quantum field theories, maybe the kind of question that I will try to answer is, what can we say about boundary conditions for Chern-Simons? And these kind of boundary conditions that we will put are of topological nature. So that's more or less the idea. And the summary of the talk is just, well, basically talk about geometry and sigma models first, then explain my result and proof, and then, well, basically consequences and related words that will be, I hope, the interesting part as well. So let's just start by the geometry. So as I already said, what we will see is these Poisson Lie groups. So what is a Poisson Lie group? Is just a Lie group endowed with a Poisson structure, and both structures should be compatible. And the way of saying that is compatible, one possibility is saying that the graph of the multiplication, it's a coisotropic submanifold inside of the triple product of the group. And the bar stands because we changed the orientation, which is the sign of one of the Poisson structures. So it is well known that Lie groups have an infinitesimal version that is Lie algebras. And now, if we put inside the Poisson structure that is compatible, the fact that it's compatible means that the Lie algebra inherits a Lie bialgebra structure. And this was proved by Drinfel'd almost 40 years ago, I think. And there are many ways of saying what a Lie bialgebra is, but basically the point of view that I will take is that the Lie algebra carries as well a Poisson structure that is linear and compatible with the Lie bracket. And the fact that that there is a duality between linear Poisson structures and Lie brackets means that there is this duality between Lie bialgebras, that something is a Lie bialgebra if its dual is as well a Lie bialgebra. And therefore, that implies that Poisson Lie groups appears in pairs. So there is a duality between these kind of objects. And that will play an interesting role in my talk. So more on this duality is that given this Lie bialgebra, I can form the Drinfel'd double. So I can just take the sum of the two things and endow it with this strange bracket that sees all the multiplication. So I have the Lie bracket on one side, the Lie bracket on the other side, and then the quadjoint actions acting one on the other. And it's really interesting that this is more than a Lie algebra. This is a quadratic Lie algebra. So it carries just the natural pairing between G and G dual. And what we can do with this is just abstract the notion of this object and define what a Manning triple is. And the Manning triple is just a quadratic Lie algebra that carries two Lie subalgebras that their sum is the total space, and they are isotropic under this pairing. And that means, and was proved by Manning, that there is a one-to-one correspondence between Lie bialgebras and Manning triples. So once I choose this Manning triple on my Lie bialgebra, then G minus becomes the dual of G plus under the pairing, and G plus and G minus becomes Lie bialgebras, and H becomes just the Drinfel'd double of G plus or G minus, whatever you want, or isomorphic to the Drinfel'd double. So these kind of objects are the ones that we are interested in to study, because right now you already seen it almost all the ingredients that I need. So we have Poisson structures, Poisson Lie groups, quadratic Lie algebras, so all these kind of things. So let's now go to, the field theoretic part. So it is well known that Poisson manifolds carries a sigma model. What a sigma model is a two-dimensional sigma model in this case, is just a space of fields that is given by vector bundle morphism from the tangent of my sigma to the cotangent of my Poisson manifold. So as you see, there are two kinds of fields, this Y and this zeta. And what is important is that they carry this action, that this just produce a number via this interaction between using the Poisson structure. And this is called topological because there is no metric involved here. So just you need the Poisson structure in order to define this object. So the important thing that, well, here we will not see it, but is that if this surface have boundaries, then the action is not really invariant under all the gate symmetries that you want to impose. Therefore, you need to impose some boundary conditions, or you can impose some boundary conditions. That's one way to treat it. And what you can do is put as boundary conditions any coisotropic sum manifold on your target Poisson manifold. And the thing that we are interested in, and that's the quantization, is this path integral. And it's just something that is mathematically ill-defined. And basically, there are many ways of trying to make sense of this thing. But what we can try to do is just make sense of this kind of path integral via the perturbative quantization, so via just the stationary phase formula. That's the hope, that's the dream, to make sense of this kind of path integral for the Poisson sigma model. And I need to say that there is one computation that is really important, and this is what motivates that this Poisson sigma model is basically interesting and can compute something meaningful. That is that if as sigma I take a disk, and as O I take a particular observable depending on two functions and 3 market points on the disk, then I can reproduce the Kontsevich star product via the stationary phase formula just by looking into these path integrants via Feynman diagrams. So that's the idea of how, for example, the Poisson sigma model can be used. And this was proved by Cattaneo and Felder in 20 years ago. So this is associated to Poisson manifolds. So we have one of the sigma models that we will use, and the second sigma model is Chern-Simons. That instead of being two-dimensional, because instead of using surface, we are using three-dimensional manifold, so it's three-dimensional. And what we have right now is that the second piece of information is a quadratic Lie algebra. So one of the pieces that we have as well once we have a Poisson Lie group. So associated to any three manifold and any quadratic Lie algebra, I can create a space of fields that are just one forms. Oh, sorry, there is a typo. This should not be this. This should be, oops, how I make this. So this should be n. So the space of fields are just, one forms on n with values on my quadratic Lie algebra. And I'm just thinking on that because basically what I'm doing is trying to, or what I want to do at some point is trying to make sense via perturbatively. But the real fields on the Poisson, on the Chern-Simons, and also in the Poisson sigma model can be defined in a more global way. And therefore, what they really are connections on principal H bundles. That's what the real fields on the Chern-Simons is. But if I take just an H principal bundle and I look it just on a trivialization, then the principal bundle becomes trivial and the connection just becomes a one form with values on the Lie algebra. And this is what we are doing here, basically. Just thinking at the infinitesimal level or locally enough what is happening. So that's the space of fields. And now the action, we can produce it as well as in the Poisson case, just by looking into this connection. So this is the classical action for Chern-Simons. And I want to say that once again, since I want to make sense of the path integral perturbatively, I don't care about the level or the associator that was, for example, appearing in Catherine's talk. So here I just picked an action and I don't care about the level, about the global aspects of how to define this action. So once again, as happens before, if the three manifolds have boundary, in order to be well-define this action and in under gauge symmetries, I need to impose boundary conditions. And the kind of boundary conditions that I want to impose are just given by subalgebras of the H whose dimension is half of the dimension of the H and they are isotropic. So as you already seen, it's like a Manning triple, but I don't have the other half. So this is called it a Manning pair. So a Manning pair gives me some kind of boundary conditions. I can impose other kind of boundary conditions, but these ones are just topological. So I can impose coming from the metric, coming from a polarization, or coming from a complex structure, and as we saw it in Pavel Nyo's talk on Thursday. That's right. And well, as before, you see we also have the path integral over here. So right now, what I just pictured to you is that we have, well, and what the Chern-Simons is important. Well, I think that we don't need to explain why the Chern-Simons is important because we already saw it in many talks here during the conference. So there are many topological invariants for three manifolds, for nodes, for many kind of quantities that Chern-Simons can compute into different ways, or looking by geometric quantization, or by looking into the path integral, or by different ways, or into the monoidal tensor category. So what I want to say right now is that all the pieces of information that we have it is given a Poisson Lie group. I can construct, the Poisson sigma model, or I can construct for the Drinfel'd double Chern-Simons or whatever, but all these things are like disconnected. So there is a way to unify the Poisson sigma model with Chern-Simons, and that way is going through graded geometry. And what you need is these AKSZ topological sigma models. So what are these data? this data is just, for a d-dimensional manifold, I need to construct, or I need to have a d-1 symplectic Q manifold. What's that? That's a graded manifold endowed with a symplectic manifold of degree d-1 and this theta that is a charge of degree d, or the Q structure, whatever. So that also doesn't tell you anything, I think. So basically what is happening is that to any manifold, a supermanifold is just something that I add some polynomial new coordinates that are just formal and they have some degrees. So what I'm doing here is just secretly homological algebra. So I'm putting just some information coming from, so I'm resolving something basically. So I'm putting just information of homological algebra, and this Q is a differential that I have on, let's say, my complex. And in addition, my complex, I want to be, graded Poisson, and this Poisson thing to be non-degenerate. So that's basically what a symplectic Q manifold is. And these are the kind of things that I need in order to cook up these topological sigma models. And the definition of them is that on the fields, I just consider the maps between T1 sigma, so just basically differential forms on sigma, into my symplectic Q manifold, into my graded manifold, into this homological thing that is resolving something. And then, as before, I need to impose some boundary conditions as well. And I also have an action, and this action is completely defined just by the choose of a potential 1,4 to my symplectic structure and this charge. So the first part of the action, this one, where it is, 10, okay. So this part is like the quadratic part, and is call it, like the topological part, and this is like the interaction part. So these two things is basically what will create the interesting properties of these AKSZ sigma models. So the important thing is that in the total space, I have a symplectic form of degree -1. And while this is important is because I want to make sense of the path integral. And the idea of path integral right now is that I have some freedom to make sense of this theory just by looking into the Lagrangian some manifolds. So I want to make sense of, let's say, the zero section, and that's not possible because it's a gate theory. So what I do is just deform the zero section into some Lagrangian, call it the gauge fixing, this LBB, and I want to make sense then of this path integral perturbatively, and that should be possible under favorable choice of my Lagrangian. And the computation will not depend on the choice of my Lagrangian by, some homological algebra as well. So this was proved by S-bars. So that's basically the idea of how this computation should work. If it works or not, or if we can make it working or not, that's another thing. So today, what I want to show you is that, well, I will pass from one to another, from one sigma model to another without trying to make sense of this path integral. But that passing from one to another will imply that, these kind of things should be somehow making sense of them. So once I introduce this general notion of topological sigma models, I want to show you that the two previous examples fit into this framework. So let's go there. So associated to any Poisson manifold, I can look just into the multi-vector fields of that Poisson manifold. And multi-vector fields, they are just, sections of the wedge of the tangent. So locally, they are just like polynomial variables into these vector fields. Therefore, this produces a graded manifold that usually is denoted by T star 1m. And that's the odd cotangent bundle as well, also call it. And what happens in multi-vector fields is that they have naturally a bracket that is the Geoquant bracket. And if you look close enough into them, it happens that the Geoquant bracket is symplectic because it's like non-degenerate, and that's basically, the Jacobi identity for vector fields on a basis that they commute, basis of vector fields commute, and that tells you that the Geoquant vector field is non-degenerate. And then the last piece of information that I need is this Q structure, this homological vector field, and that's just bracketing with the Poisson structure. This happened to have degree 1, and this is what it's giving to me, this resolution of something that eventually will be the quotient of the symplectic foliation. So somehow what this is more or less, the homological algebra that is behind this is just the leaf space of the symplectic foliation. This is more or less what is modeling here in this case. So how this fits into the AKSZ sigma model is just, I have a degree 1 symplectic Q manifold, therefore I have a 2-dimensional sigma model. And what happens is that right now the fields are maps between T1 sigma and T star 1 M. And then the action becomes, the action of the Poisson sigma model plus some terms on antifields. What are the antifields? Are the ones that are here denoted by a plus. And the classical fields of the Poisson sigma model, that's it. The part that we already saw it in the previous slides is just the ones that they are marked in blue here. And why I need to add all these fields is because, I want to make something symplectic of degree -1, and therefore the plus is stand by the symplectic conjugate of my fields, and this beta basically will give me the gauge transformations of the vector fields. So I'm just included the vector fields, their gauge transformation, and then take it basically an odd cotangent bundle of that. And that's what the Poisson sigma model in this AKSZ form all codify. And the higher terms here in the action will codify that interaction between, the symmetries and the homotopies for the symmetries and these higher terms. Analogously, given a quadratic Lie algebra, I can just take the H shifted by 1. That's it, just, the stereo algebra of H star. And as before, this is a super manifold. And I think in the coordinates here on H star are shifted by 1. And therefore, they have degree 1. The generators have degree 1, is what I mean. And now the magic here is that the pairing of the quadratic Lie algebra can be shown as a degree 2 symplectic structure here. And here is crucial that the pairing is non-degenerate. That's the fundamental thing why this is symplectic. And the differential is just, the usual Chevalier-Eilenberg differential of the cohomology of the Lie algebra. And this is how all these things are related and they are compatible. And then I can make it just the same. Right now, the space of fields will be maps from T1n into H1. And as well, the action will have more terms. And as happened as before, the classical part is just the field marked in blue, this A. But I need to add the symmetries that are C in this case, and the antifields for all them. So the last thing that I want to say is that if we are in the case of a Manning triple, as I already say, Manning triples can be identified with Lie algebras. And therefore, I have an isomorphism between H1, this graded manifold, between this horrible...
Miquel, just here.
Sure.
So this in your third to last line, is that the construction by Roger and Lecomte, which was later called by Kosman Schwarzbach the big bracket, le grand crochet?
Perfectly, yeah, you can show it as that. That's it. Mm-hmm. Yeah, so this curly bracket is what is called the big bracket. Yeah, that's right. So in the case of the Manning triples, I already say that the H can be identified with, the Drinfel'd double of G plus or G minus, and therefore I have this isomorphism that doesn't looks a bit intimidating at the beginning, but it doesn't tell me anything. But it's important that right now I can divide the fields, not just all the fields, in fact, into the part that have values into A plus and the parts that have values into H minus. And this will be important to our play. So right now we already have all the ingredients that we need. And basically, I can go to the second part of the talk that is explained to you, which is our result and a bit a grasp on the proof. So basically the question that we have here is, which is the relation between the Poisson sigma model on the Poisson Lie group and the Chern-Simons on the Drinfel'd double. And the result is that basically you can be a bit more general and just start with a main triple, and then consider a closed surface times an interval, and took Chern-Simons on the closed surface times the interval, the target, the H of the main triple, and the boundary conditions, you put it one of the two Lagrangian subalgebras, or H or G plus or G minus. And then what happens is that, for example, if we put G minus on the two boundary conditions, we put the same, then it happens that this Chern-Simons theory admits an effective theory given by the Poisson sigma model on the other that integrates the other part of the Manning triple. So in this case is the integration of G plus with the Poisson Lie group structure on G plus. And I need to say that this G plus is the connected and simply connected integration of G plus. So it's the maximal one that can integrate. So I'm not explaining too much what is an effective theory. So let me try just by computations explain what I will mean by this effective theory. So the first thing that we need to show is basically what happens with the mapping space. And as I already said, the mapping space, so the space of fields on Chern-Simons with this extended point of view of Batalin-Vilkovitsky, it takes place in this T1 or sigma cross the interval into H1, and then with this isomorphism with the Drinfel'd using the Manning triple and the Drinfel'd double, then I get this other isomorphism with this other space of fields. And now what I can do is use the exponential property of the mapping space between supermanifolds in order to put one of the factors inside. And which factor we choose is the interval, as opposite as we saw it in the Pavel talk, that he did it exactly the opposite. He put it inside sigma. So what we are doing is exactly the opposite as we saw it on Tuesday. And that's basically the exponential properties of the mapping space. It's nothing really intimidating. So right now here is what I mean by an effective theory. And I hope that will be more or less clear. So the idea is that this formal path integral should give what the computations on one side can be done into the computations of the other side. So basically, we are going from this Chern-Simons here on the top to the Poisson sigma model in the bottom, just by, a coisotropic reduction into a symplectic manifold that is this N. And this is why it's an effective theory, because there is a coisotropic reduction on the middle of the step and of this N manifold, and that's the K part. So this N admits a coisotropic reduction. That's the message that I want to say. And therefore, the reduced space, it's an effective theory for the big space. And the point is that this can be made compatible with the AKSZ construction, and this was shown by Cabrera, Bonecki, and Sapsin. And the last part is just recognizing that this reduced theory that you have is the Poisson sigma model action. So let me say just a bit of why this reduced thing should be the Poisson sigma model. So basically what we are looking is into T1 of the interval that we can split into two other manifolds, the interval and R1. And if I put R1, then just a tangent shifted by ones appear. And therefore, I can think this space as path into a tangent of a cotangent of whatever. So something difficult. But what it happens is that this difficult thing, it have a double vector bundle structure, and this double vector bundle structure allows to put an additional grading. And this additional grading, it's an homological way of making reduction, basically BRST. So once again, we are doing just homological algebra with a flavor of geometry. And therefore, it's really easy to see that the zero part of this is just the path space of the cotangent of G plus. And then just produce reduction there via just, path, Lie algebroid path modulo Lie algebroid homotopies. And then this is why it's appearing in the group of G plus. So that's basically the idea, that the coisotropic reduction is just happening in the path space. So with that, I want just to say that our theorem, we can change Poisson Lie groups by Poisson groupoids, Lie bialgebra by Lie bialgebroids, and now the Drinfel'd double also have a double, but right now it's a Courant algebroid. We can also have a notion of Manning triples for Courant algebroids. And the definition of a Courant algebroid is just something that have a metric compatible, but the bracket is not skew symmetric. This 4 property is what is spoiling me the skew symmetry of the bracket. So the result can be made it more general. Just for any Manning triple on a Courant algebroid, we have that the Courant sigma model admits a dimensional reduction into a Poisson sigma model with a Poisson groupoid given by the opposite of the boundary condition that we put. So let me just go into the last part in the 3 minutes that I have. So basically, the first thing that I want to say is that what we are doing can be done just in a color neighborhood of any boundary that you choose. So this is telling you how the theory on the boundary, once you fix a topological condition of this kind, is behaving. So basically, you can reduce the bulk theory to the boundary, and in the boundary is appearing a Poisson sigma model. The second interesting thing is that there is this nonlinear versus linear duality. So on one hand, we have something that is 2-dimensional with a Poisson Lie group that is not linear and no boundary that is good. But on the other hand, we have a 3-dimensional theory on a target that is really linear, but with boundary. So this kind of duality, it tells us something that maybe, it's a good idea into Poisson Lie groups to look into just the Manning triple in order to quantize them. And that's already known, as I will say at the end. And then there is another thing that we can do, and this is the other kind of duality by switching boundary conditions. So if you switch boundary conditions, then the kind of Poisson Lie groups so you obtain 2 different effective theory, and maybe there are observables that are reducible by the 2 effective theory, and then you can try to interplay some kind of observables between one and the other. For example, trying to compare the Kontsevich star product on a Poisson Lie group and its dual. But that's just one idea. And then the last thing that I want to say in this slide is that our theorem is topological to topological, as opposite from the usual that is Chern-Simons to Wess-Witten that is conformal. So that's the usual, normally holographic relation that people find in the literature. So let me just end with some related works. So I want to say that when the Lie bialgebroid is trivial in some sense, so when the Poisson structure of the Lie bialgebroid is 0, that case was already known and was made by Catania, Geoquant, Sapsin almost 10 years ago or even more. The second thing is that this kind of boundary conditions was also studied by Severa, and he also have other kind of non-topological boundary conditions given by generalized metrics on Courant algebroids. And well, as we already saw in the talk of Pavel, he's also using another kind of boundary conditions that are normally free boundary conditions, and also polarizations. And finally, what I want to say is that the quantization of Lie bialgebras was already done by Ettinghoff and Kasdan of the let's say the universal quantization of Lie bialgebras was done by Ettinghoff and Kasdan many years ago, using the Drinfel'd double and finding them inside them these Berman models that really resembles to the kind of boundary conditions that we are considering. And yeah, that's everything. Thank you very much.
Thank you very much. Are there any questions from the audience?
So if you describe transassignments on something that is of the form sigma times some interval, in principle, you're quite close to the moduli spaces of flat connections on sigma. Is there some way of translating your picture? So if I think of moduli space of flat connection on a surface, I think, okay, you have the generators of the fundamental group, you have one group element for each of them, and so on. So I think in a sort of discrete way. Some way of going from formalism and translating this correspondence with the sigma model in this way, or is it?
That's a really good question. So I don't know. What I can say is that if in the Poisson sigma model you pick a square, then what happens is that the moduli space of solutions that appears there is the symplectic groupoid integrating the Poisson manifold. So I will expect that here, there is something like this. So I have one Poisson-Lie group here. I have another Poisson-Lie group here. I can put a point here. And then there is something that is the double symplectic groupoid integrating, oops, that was an S, whatever. So there is a double symplectic groupoid that integrates that. So what I expect is that if sigma is a square, probably the moduli space of flat connections is this double symplectic groupoid. And then you have the two legs put in some kind of boundary conditions in the moduli space, give you one of the Poisson-Lie groups. If you put the other boundary condition, give you the other one. But that's just for a square. For a general sigma, I have no idea. And that will be really interesting.
Maybe one could treat this by gluing.
Yeah, maybe it's a good idea. Sure.
Thank you.
So thanks again for your brilliant talk. So I really enjoyed it. Just a completely naive question. I mean, you wrote down, and I should know this, but I don't. You're talking about these Courant algebroids, right? If I compare them to Lie algebroids, of course, that's a different world. But in Lie algebroids, you have, for Lie algebras, you have, say, the category of associative algebras, and you have the functor which associates to an associative algebra, the Lie algebra by its commutator. For Lie algebroids or Lie-Reinhardt algebra, you have the same thing. Then you take associative algebra over a commutative ground ring, and this is thought of as a sort of sub-algebra, but not in the center, etc. And then there is also more complicated. In both cases, the universal objects are left adjoint functors. Question is there something for Courant algebroids? Is there some algebraic gadgets which serves as the sort of algebraic integration analog of this, so that one can find these universal objects?
So I don't know so much about that, but I can say something that is the kind of things that is expected that one should find here is that basically the quantization of Chern-Simons, the geometric object associated to that, is like a 2-gerb. Or you replace the line bundle with connection with a 2-gerb. And if you want to find something like a deformation or something like that, there are these EN algebras And what you should find, I think, if I'm right now, I don't know, I think that is an E3 algebra. That should be the kind of things that quantize this, this kind of objects. So for Courant algebroids, I think that should happen the same in general. So at the classical level, what is conjecture is that what will appear is just a two-shifted symplectic two-groupoid. That's the classical object that integrates this kind of Courant algebroids. And at the quantum level, well, there are many kind of proposals. Maybe one is these higher gerbs, two kind of two gerb, and some kind of polarization there, or this kind of EN algebras, so E3 algebra or something like that. I don't know if it really answered your question, but yeah.
Thank you.
Thank you.
Any more questions? If not, then thank you again very much.